Hello, this is Andy Schweitzer, and this is a additional video in a series of videos that are discussing states of matter. Currently, we're looking at solids, and the question we're looking at here is why is a solid a solid? And we already discussed some of the internal factors. And when I say internal, I mean bond types. And in this video, we're looking at what I refer to as external factors. Now, these are factors that you can control. Okay, so as far as external factors, what can you do to make a solid or liquid? And in this case, there are two of them. One is going to be temperature, and the other one is going to be pressure. So we'll take just a few moments, and I'm not going to go into huge depth over these concepts, just a little bit, just to kind of give you a heads up on how this works. Okay, so what is temperature? And we'll talk about temperature quite a bit more in class. What are the basics you got to know about temperature? One, it fooled human beings for thousands of years what temperature actually is, and it is basically the movement of particles. Another way of saying this, it is the average kinetic energy. So if we have a solid just, on a dish, and this thing is stacked up here, there's particles inside this thing. If we blew it up, we'd see these particles, and they're connected to each other, by whether either ionic bonds or whether they're connected by intermolecular forces. They are rotationally moving, vibrating back and forth, but not really moving translationally or cross anywhere, but there is movement. Some of them are moving more than others. So we say average, meaning some are faster, some are slower, but it's average movement of particles. This is temperature. Kinetic energy is described as Ke, which equals kinetic energy 1/2 the mass velocity squared, and we'll use that more on in the future. Okay, so essentially, what happens as you raise the temperature up, you increase the movement, and eventually this movement shatters the intermolecular forces or the ionic bonds, and then causes, for a solid, would be melting. Okay, in this point here, it's pretty simple. We'll just take a moment to discuss some of the temperature scales. Okay, we have the Fahrenheit scale, we have the Celsius scale, and we have the Kelvin scale. Now, whenever we're dealing with a measurement system, there are inherently two different types of measurement systems. There is what's called a relative scale and an absolute. Okay, some things are easier to measure than others, and temperature has been a tough one. The Celsius scale and the Fahrenheit scales have been based off of historical things like the melting point of water, the temperature of the human body. Fahrenheit was a medical doctor. Celsius was a scientist. This scale is something he was working on, and ended up passing away before it even became real popular. But he based his scale essentially off of the 0 being the freezing point of water, and 100 as being the boiling point of water. And then, of course, put 100 just arbitrary units between there, and that's his scale. If you look at the actual idea of temperature as being movement, can you have a negative temperature? Yes. Can you have negative movement? No. So this is a relative scale between, I'm going to go from 0 to 100. This goes from 32 to 212, and these are identical temperatures. So there is linear relationships. If I move up 5 units of degree here or 5 units of degree here, doesn't matter. It's the same difference of temperature. Same thing for Fahrenheit. I will say that a degree Fahrenheit is smaller than a degree Celsius. So if I raise a room 10 degrees Celsius or 10 degrees Fahrenheit, that's not the same quantity of temperature. Now, Kelvin is what we call an absolute scale. And again, once we learned more about temperature, this was a possibility. In Celsius's time or Fahrenheit's time, it just wasn't a practical possibility because you don't even know what temperature is, much less how do you create an absolute scale for it. So in this case, scientists have basically determined that temperature is in fact movement. Therefore, there should be an end point or a bottom point for movement. And we call that absolute zero. Okay? And whether we've actually reached absolute zero or not in labs, it's been interpolated that at negative 273 degrees Celsius, okay, is the lowest possible temperature, and they will set that at 0 Kelvin. All right. So at this point, the absolute bottom temperature would be negative 273, and they adopted the Celsius scale for their increments. So this would be 0, and this would be a positive 273. All right. Therefore, the boiling point of water would be 373. So note that the amount of increments of the Celsius scale are the same as the increments for the Kelvin scale. At this point, you could do a mathematical relationship between the two. The Celsius plus 273 equals the Kelvin. Doing mathematics with Celsius involving negatives is an issue. Therefore, sometimes it works, but for the most part, Kelvin will always work. Kelvin will always work. And I don't really know the bottom temperature. It's like negative 400 something, but we don't really use this other than for our daily American lives of temperature. Okay. For the use of this particular idea, we will be looking at a melting point curve. And give myself a little bit of room here. All right. We have what's called a heating curve, and it's going to show how temperatures affect on a substance. This is the heating curve, and on the bottom here we're going to show could be described many ways. Could be movement, could be time, could be distance between particles, whatever. And on this side here, we're going to go temperature. Okay. And it looks essentially like this. Okay. If this is water, this would be a solid, liquid, and gas. This, again, for water, H2O, would be 0 degrees Celsius. This would therefore be 100 degrees Celsius. In my class, we've already discussed this curve early on, just in phase changes. But you should, so I'm not going to discuss all the phases and whatnot, but you should understand that there is a certain amount of energy needed to jump from a solid to a liquid, and vice versa. I've also talked about this in a previous video just a little bit ago, but in this case, low energy, and as we go up, this way we are adding energy. Okay, as we come back down, okay, energy is being released. So something going from a gas to a liquid, it's slowing down, has to ditch off some energy. Energy is being given away. In this case, energy is going in. Okay. When you sweat, your liquid sweat goes to a gas. Energy needs to be added into that to get that to go to a gas, and that comes from your body, therefore cools yourself. Either way, in this case, the energy between a solid and liquid is called delta H, and this is just heat energy of vaporization. Sorry, not vaporization, that would be the next one, is called fusion. Same amount of energy that causes it to go solid liquid is the same goes from liquid back to solid. So it's a revolving door. It's just simply conversion from H2O solid to H2O liquid. Certain amount of energy needed. So as I add energy to this thing, I raise up temperature, and then I stall out here because all the energy I have adding at this point is utilizing this conversion to a liquid. Once I'm in a liquid, I can raise up more temperature, and then I can use energy to go from a liquid to a gas. This is called delta H of vaporization. And we'll do maybe some minor calculations with this. It's more, I might deal with this more in thermodynamics. Okay. Either way, you should be aware they would simply do it at this point in an energy like a kilojoule per mole. And it would say, okay, if I have 1 mole, it takes so much energy to flip it from a liquid to a gas. Simple linear proportion. You could use a ratio to solve this. But either way, our next factor we're looking at is going to be pressure. Okay. Now, pressure is something that doesn't affect solids as much, but it does have effect on them. So what is pressure? Pressure is equal to force per area. There's a lot of analogies of pressure. If someone steps on your foot with a regular pair of shoes on, or they step on your foot with, let's say, high heels, in that back part of the high heel, you have the same amount of force, but in a smaller area. Therefore, your pressure is driven up. Okay. Either way, pressure does have effects, and whether we have a solid, liquid, or gas, it affects them differently, but still has effects. Our main unit of pressure, and again, I'll talk more about pressure during gases, but main unit of pressure is what we call atmospheres. ATMs, or atmospheres. And the other one would be millimeters of Hg. And again, I will talk more about these and how they got this in gases. But for this point, we have the Earth, and if you are standing on Mother Earth, there is a column of gas above you, and all those gas particles are also attracted to Earth by gravity, just because same as you are, and they are putting pressure down on you. And this amount of pressure is called the atmospheric pressure, and this is where we would be using pressure. Either way, it has been determined that the atmospheric pressure is about 760, equivalent to the weight or the force down of 760 millimeter of Hg. So a column of mercury, which is much smaller, okay, 760 millimeters, has the same force down as the entire atmosphere. And of course, it changes day to day because we have different compositions of atmospheres above us. But it's a unit of measurement of pressure, and this is equal to 1 atm. Okay. One way we will use to sort of quantify this or to look at the effects of pressure is going to be what's called a triple phase diagram. Every substance has a triple phase diagram. It shows the relationship between temperature and pressure. You should note that increasing temperature is going to drive you from a solid to a liquid to a gas. You should also note that increasing pressure would be just the opposite. It's going to drive you from a gas to a liquid to a solid. It's going to drive particles, increasing pressure is going to drive them together. Not nearly as effective as the pressure, as the temperature. Temperature is really good at expanding things out, making liquids to gases and stuff like that, but it is nonetheless. So let's just draw out a simple triple phase diagram. Very easy to look at, see, interpret. Okay, looks something like this. Okay, and when you see problems like this, this will be an arrow. This one will go on and it will actually stop here. All right. They'll have pressure on this side, and they'll have temperature on this side. Just a quick little highlight here. This is the solid region, this is the liquid region, this is the gas region. And they're not guaranteed to give you these solid, liquids, gases. Okay, you need to know that. We have a pressure, let's say it would be 1.0. This is referred to as normal pressure. They're referring to ATMs. This point right here is often referred to as the triple point. Okay. This is not an arrow, it's a dot. They call this the critical point. The triple point is where all three phases are present. Solids, liquids, and gases. Seems strange, but under certain conditions, unlike on Earth, you might have this take place. Whether it be at a very lower pressures, certain temperatures, all three could exist. Critical point simply states that there is the temperature is so high that we really having no pressure can keep a liquid. So it's kind of a fuzzy-ish area here, but eventually it just like blends in here and you become only gases beyond sort of this region. Other than that, you should note that this line here, whenever we give let's say a 1 atmosphere pressure, if you want to find the melting point, this is referred to as the melting line. This is the boiling line or the vaporization line. And this is the sublimation line. So if you want to know a boiling point or a melting point, you simply say, okay, well, give me a pressure. I'll say 1, it's standard. Come across here, catch the melting point line, and come down. This is at this pressure, this is the correlating melting point. At this temp pressure, this is the correlating boiling point. Is there a sublimation point here? No. Drop the pressure down, let's say 0.5 atmospheres, then you come across here. This would be the sublimation point, which at that point wouldn't have a melting point or a boiling point. So, triple phase diagram describes the relationships between temperature and pressure. That's the end of our external factors.